so we're just going to continue on with this idea with exponents and logs. And we have this table here, and our goal is to try to figure out what the pattern is. So when I put in 8, I get out 3. When I put in 32, we aren't sure. When we put in a half, we get -1. We have some more x values we're unsure of. When we put in 64, we get 6, and some more x values here. So just taking a look at this, if we were trying to fill this in, we know we've been working a lot with some exponents, and so maybe I can raise numbers to certain powers to try to get these things. So for example, we know that 2 to the 3rd power is 8. Let's see if that works on this next one. 2 to the -1st power, that is the same as 1/2. And 2 to the 6th power is 64. So an equation that we could write that relates x with g of x, we would say x equals 2 raised to the g of x power. So we know our x value ends up being 2 raised to this value. So let's try filling in the rest of the table with that pattern now. Here I have 32, so I want to know 2 raised to what power gives me 32? Well, we know 2 to the 5th power gives us 32. 2 to what power gives me 1? Anything raised to the 0 power will give us 1. We know 2 to the 4th power gives us 16. 2 squared gives us 4, so 2. To get 3, we'll come back to that. To get 2, we know 2 to the 1st power is 2. If I want to get 0 as a result of something, 2 being raised to something, it is impossible to get 0 because 2 to the 0 is always 1. Anything raised to 0 power is always 1. And if I did a negative number, like -3, that's the same as 1 over 2 to the 3rd, which is 1 over 8. There isn't positive values, 0, or negative values that will ever give us 0, and that makes sense because when we graph an exponential function, we have an asymptote along y equals 0, essentially because if you keep taking a number and you cut it in half, you won't ever get nothing, so that would be undefined. All right, with 0.25, we know 0.25 is the same as 1 over 4, and 1 over 4 is the same as 1 over 2 squared, which is the same as 2 to the -2. So we know that this has to be -2. Let's check out -1. -1, again, this is saying 2 raised to some power equals -1. Because I'm raising 2, which is a positive base, to some exponent, I can't ever get a negative, so this is also undefined. For the square root of 2, we have 2 to what power gives us the square root of 2? Well, we know square root of 2 is the same thing as 2 to the 1/2, because this is 2 to the 1st power, and a square root is what times itself gives you that number, so this is the same as 2 to the 1/2. So we know that that would have to be a half, okay? 0.2, we will come back to that, and then let's look at 1 over 8. We know that 2 to the 3rd is +8, so if we do 2 to the -3rd, that would give us 1 over 8. To get an x of 3 and an x of 0.2, let's pull up Desmos to try to kind of play around with how close we can get to those values. Okay, so here we have Desmos, but the scientific calculator pulled up. If you just Google Desmos scientific calculator, or if you just do www.desmos.com/scientific, it will take you here. So again, the question is 2 to what power will give us 3? Remember, to get an exponent, you'll do Shift-6, and that will raise you into an exponent on your keyboard, or you can also click this button, a to the b power, and that will also raise it for you. So we're just going to type in some numbers and see if we can get close to 3. 2 to the 3rd is 8, so we know it has to be smaller because we want our number here to equal 3.
So if I try 2 to the 1st power, it equals 2.
And 2 to the 2nd power equals 4. And so if we want it to equal 3, we know that our exponent will have to be in between 1 and 2.
So I'm just going to go an even in between of 1.5 and see what that gives me. And that gives me 2.82, which means I'm getting close to 3, but I still need to go up a little bit on my exponent.
2 to the 1.6 power gives us about 3.03, which is pretty close. We could make this maybe like 5.5. That's getting closer, maybe 5.6, 5.7. What about 1.58 power? 1.59. So yeah, almost 1.6, maybe a little bit less than that. So, but that's pretty close to 3.
So we found that 2 to approximately 1.6 gives us a 3 value.
Let's use that same method to figure out what exponent we need to get us an output of 0.2. So our goal again is to make 2 raised to whatever power it is equal to 0.2.
If I do 2 to the 1/2, I get 1.4.
We want it to equal 0.2, so we will want a number even smaller than a half. Let's try 2 to the -1. 2 to the -1 gave us 0.5. Okay, so that's getting closer, but we want a number even smaller than -1 if we want to get down to 0.2. So maybe let's do 2 to the -4. 2 to the -4 power is 0.06. Okay, that's a little too small because we want it to be 0.2. So maybe let's go a little higher, 2 to the -3. That gave us 0.125. We're getting closer to the 0.2, but we're not quite there yet. Let's try 2 to the negative 2. Okay, that's 0.25. That's really close to 0.2. So maybe let's do 2 to the negative 2.1. Let's see where that takes us. That gives us 0.233. Okay, that's getting close to 0.2. Maybe we can raise it up a little more. 2 to the negative 2.3 gives us about 0.2. That's pretty close. So we saw that 2 raised to about negative 2.3 gave us approximately 0.2. So looking back at our ancient puzzle, how could we rewrite this equation so g of x is not in the exponent anymore? If we think back to our ancient puzzle, we had something like 2 cubed equals 8. And so if we did log base 2 of 8, then that told us what exponent we need to raise the base to in order to get that inside. So if I'm doing that here, we know we're going to work with g of x, that's our output, that's our y equals, g of x equals log, and our base is 2 of x. So we know log base 2 of x is the inverse of 2 to some power. So our original function, x equals 2 raised to g of x, we know that g of x, because that's our exponent, that's whatever our log of base 2 of x equals, because 2 raised to g of x gives us whatever is on the inside that we need.
Our next question says, why is it difficult to think of an output for the input of 0 or negative 1? So if we look up at our table and we look over here, why is it difficult to think of an output when I put 0 in or negative 1 in? So why is it difficult? Well, because the outputs of these values don't exist. It's undefined. There is not an output for these values.
We can't raise 2 to some power to get us 0 or raise 2 to some power to give us negative 1. If we think again about an exponential graph, there's that asymptote at y equals 0. And so you can't ever equal 0. You get closer and closer to 0, but you never cross it. And you can't have negative 1 as an output either because we're only looking at 0 on up to infinity.
And then our last question is, what is the output for x equals 25 to the nearest hundredth? So my g of 25, what would that equal? So we're going to write this in here, log base 2, we're still using 2, of what number? Well, that's 25 because our 25 is replacing our x value. So now we need to know what value would log base 2 of 25 equal. If we think about that in exponential form, I'm going to place my x is my answer, and that equals 2 to some power would equal 25. So 2 to what power? Well, I know 2 to the 4th power is 16, so we're somewhere in between this 4 and 5. Let's pull up Desmos to check it out.
Like Janice mentioned earlier, we know that our exponent has to be between 4 and 5 in order to get that output of x equals 25. So let's try 4.5 right in the middle there. That gives us an output of 22.62, so maybe a little bit higher. Let's try 4.6. All right, that's pretty good. 4.6 is 24.25, and they want the nearest hundredth, so that means we can do like one more number after the 4.6. So maybe let's do 4.62. 24.59, we're getting so close to 25. Let's try 2 to the 4.63. Okay, that's 24.76. That's even closer. Let's try 2 to the 4.64. That's 24.933. That's really close to 25. Let's see what happens if we did 2 to the 4.65. All right, and that puts us a little bit over 25 here. So we know that about 4.64 would be the exponent we would want. 4.64 is pretty close to the 25.
So that means that g of 25 is approximately equal to 4.64.
All right, we're going to continue on with our ancient puzzle here with Lynn. Lynn is supposed to fill in this table for g of x equals x. She thinks she can use the log button on her calculator, but when she tries to enter 5, 25, and 125, she does not get the output the table below displays. She's fuming how long it's going to take to guess and check each one, when her sister suggests that she does not have to do that for all of them. She can use what she knows about exponents to fill in a couple more, and then she can guess and check to fill in the others. Here we know when we have an x value of 1/5 that g of x equals negative 1. We know that when our x equals 1, our g of x equals 0. We know that when our x value is 5, that our g of x equals 1. When our x value is 25, then our g of x is equal to 2. And when we have an x value of 125, we have a g of x or a y value of 3. So we can kind of see the pattern pretty easily. We know 5 to the first power is 5. 5 to the second power is 25. 5 to the third power is 125. 5 to the 0 power is 1, and 5 5 to the negative 1 power is 1 over 5. Here on part A, it says, discuss with your team which outputs can be filled in without a calculator. So let's talk about the outputs that can be filled in without a calculator. We'll just circle them as we go. So 1 over 25 isn't that hard to fill in without a calculator because we know 5 to the negative 2nd power is the same as 1 over 5 squared, which is 1 over 25. 1/2 might be hard, 2 might be hard, 3 might be hard, 4 might be hard, 6, 7, 8, 10. But these upper ones won't be hard because we can express these as powers of 5. We know 5 to the 4th power is 625. And all these pre-filled ones also weren't too bad, not only because they're given to us, but we can see easily, that's easy to express the x value as an exponent of 5. 5 to some power gives us that output. The way we'll fill those in without a calculator is we know that 5 to whatever output was, g of x, has to give us our original x value. So 5 squared is 25. 5 to the 4 is 625. 5 to the 3rd is 125. So that's how we were able to fill those ones in pretty easily. To find out some of these ones, we're going to have to pull up good old Desmos to figure out what works. Luckily for us, this is all in order. So we know that to get 5 to something equal to 1/2, we know that number has to be between -1 and 0. So let's pull up Desmos and try to fill that one in. We have our base of 5. We're going to raise it to some power between -1 and 0. So let's try -0.5. When we do that, we get 0.44, which is pretty close to a half. So maybe let's try a higher number. Maybe let's do 5 to the -0.6. All right, this takes us further away from 0.5, so that means I need to go smaller than -0.5. So let's try 5 to the -0.4. Ooh, yeah, that's pretty close to 0.5. Maybe let's add an extra digit afterwards. So maybe let's do 2. Ooh, that's pretty good. 0.508. What if we did 0.43 instead? So -0.43, that got us even closer, 0.500. So let's say -0.43.
All right, so with Desmos, we found that this 5 raised to approximately -0.43 will give us 1/2.
Let's try this for maybe 100, and then we'll just have the other ones kind of filled in later. So I want to figure out 5 to some power gives me 100. I know 5 squared is 25, and 5 cubed is 125, so my number has to be in between 2 and 3 for my exponent. All right, let's try 5 to the 2.5, so that's kind of right between 2 and 3. All right, that gives us 55.9, and we want to get 100, so we know it needs to be higher than 2.5. Let's try 5 to the 2.7. Okay, that gives us 77.129, a little bit higher to get 100, so let's do 5 to the 2.8. Ooh, that's 90, that's close. All right, let's add another digit afterwards, so maybe 2.82. All right, that's 93, maybe let's try 0.83, okay, 0.84. Okay, we can keep going up. Ooh, right here between 6 and 7 is right where that cutoff is for 100. So we have 2.86 is 99.78. That's pretty close to 100. Maybe we can add another digit afterwards. We did 5. That's a little bit too high at 100.5. 3 is a little bit too high afterwards. Let's do 2.862. That's pretty close. What about 2.861? Yeah, so about 2.862 is pretty close to that 100 that we're looking for.
So we know that 5 raised to approximately 2.862 gives us 100.
All right, we're just going to fill in these other ones. You can kind of tinker around with it, but 2 raised to about 0.43 gives us 2. 2 raised to the about 0.69 power gives us 3. 2 raised to the 0.87 gives us about 4. 2 raised to about 1.12 gives us 6. 2 raised to 1.21 gives us about 7. 2 raised to about 1.3 gives us 8. And 2 raised to about 1.44 gives us 10. This might be easier if you just have a calculator like this, or you can just try typing in a bunch of numbers, or on Desmos Scientific where you can do that.
Part B says use your calculator and properties of exponents to estimate the remaining values of g of x to the nearest hundredth. So we've done the first part of B, which is fill in the rest of our table to the nearest hundred. Once you have determined several of the missing outputs, use your knowledge of exponents to write an equation related to x and g of x. So we know that our g of x is the exponent that we're raising 5 to in order to get x. So let's start with this equation here. So 5 to the g of x power equals x. Thinking through that, we can turn that into a log equation that we've been using. So let's think about our log equation. Our log is what power we're raised to. So g of x equals log base, our number that we're raising to a power. So base 5, and then whatever that equals goes in these parentheses. So we're saying g of x equals log base 5 of x.
And just like Janice mentioned, this just tells us what exponent do we need to raise 5 to in order to get that inside of x piece. All right, part C here says, what do you notice for the results of g of x as x increases? So here here, x is increasing. And what do we notice about g of x? We see that our exponents here are also increasing. So as x increases, g of x increases. Now that we have our table, let's sketch a graph. This is kind of cool because this is, well, I guess we saw it before, but we didn't know it was called a logarithmic graph, but we can kind of see what a log graph looks like. So let's just plot a few of these points. I go over 1/25 and down -2. So really small. It's right there. Go over 1/5 down 1, over 1/2 down 0.43. I'm gonna use some bigger numbers that aren't so decimal-like. Over 1 up 0, over 5 up 1. I go over 10, I go up about 1.44. Okay, so we can see as my x values get smaller, closer and closer to 0, my exponent is gonna get way larger. So this is just gonna plummet down onto -infinity here. So we have that asymptote going on again, but this time it's vertical. All right, here it says, how does our graph compare to the graph of y equals 5 to the x? So if I think about y equals 5 to the x, we know that that's just going to be an exponential graph, but our base will be stretched up a little bit higher, but not by much. And so we can see that this is just a reflection of the y equals 5 to the x graph just over y equals x. Just like we saw before, when we reflect an exponential graph, we end up with that logarithmic graph. So y equals 5 to the x. When we reflect that over y equals x, we end up with y equals log base 5 of x. So that's what this orange graph represents here.